VLSos here. This is a video lesson on differentiability, whether a function is differentiable or not at any of its locations. The best function to think about differentiability is the familiar magnitude function or absolute value function that has a corner. The magnitude function is not differentiable at its corner. But why? Well, to talk about where a function is differentiable, let's first think about where it is not. And this first thought is informal because we're going to approach it with the graph and visualization. This function is not differentiable at its corner. Why? Well, we can't linearize the function at 0. We can't have a line approximate the curve. The tangent to the curve isn't going to work here. If we zoom in at this location, it remains a sharp corner no matter how much we zoom in. It doesn't smooth out and start looking straight. Another informal thought that we could have, why we don't have a derivative here, is to think, well, where would we put the tangent line? Tangent line to the curve is going to graze the curve and intersect at only one spot. But at a corner, I have lots of options for that. I could put a tangent line in an infinite variety of ways with an infinite variety of slopes. And because there are so many places to put a tangent line, there isn't one obvious place that it needs to be, and therefore the derivative doesn't exist. So informal thoughts. Don't know where to put the tangent line since there's so many options, and we can't zoom in and linearize it. But how do we formally justify that there isn't a derivative there? The formal justification for differentiability is that a function will be differentiable where the definition applies. So a function is differentiable where the limit as h approaches 0 of f of x plus h minus f of x all over h is a calculation that shows us we have a derivative. Applying the definition of a derivative to an infinite number of points to show where a function is differentiable there is inhumanly complicated. Take too much time. So we approach finding that a function is differentiable by having an idea of where it is not. We have an idea where this function, if we define it as the magnitude function, the absolute value of x, this function ought to be able to be proved that it is not differentiable at 0. So how would we do that? We would go about using the definition by replacing the function notation with the absolute value of x. And if we did that, how would we proceed with the algebra? The absolute value of x is a little bit unique because it depends on the sign of x to determine what the outcome of the function is. In other words, we could express the absolute value of x function as a piecewise function that has two distinct pieces. So the outcome of the function is dependent on the domain, what piece you're going to use. The absolute value of x is x for all positive values in 0 and negative x for all negative values. Different piece means a different function. So if we're going to use the definition here, then we have to have two different approaches. We have to use one piece for negative values and one piece for positive values. In other words, at 0, we would be thinking of the derivative approached from the right and the derivative approached from the left. as two separate calculations. This is similar to an absolute limit where the one-sided limits are equal, yes, because the derivative is a limit. The derivative calculation is literally a limit calculation. So if we have one-sided limits and an absolute limit where the one-sided limits can be shown to be equal, then it's the same to say that we have a derivative where we can show that the one-sided derivatives at that point are equal. Let's do this calculation. If I let h approach 0 from the left of the function, the approaching from the left means that the x values are going to be negative, then I'm using this piece as the function and make the composition negative x plus h minus negative x. Again, we're using this piece to be the function and form the composition with the one-sided limit. So this becomes a one-sided derivative. And we're going to use the other piece for approaching 0 from the right, where the x values are positive. And that will be x plus h minus x all over h as the limit of h approaches 0 from the right. Let's simplify these expressions and take the limit. Distributing the negative, I have negative x minus h minus negative x. Subtracting a negative means positive, so the negative x plus the x will cancel out, leaving this negative h. It's negative h because we're distributing the negative. And the negative h divided by h is 1. And the limit as h goes to 0 then doesn't affect that constant negative 1. That reasoning again is this negative x cancels out with this subtracting a negative x, and the negative h over h makes a negative 1, whose limit is still negative 1. This expression here, x plus h minus x, makes the x's cancel out again. H is positive, so we have a positive h over h, and it doesn't matter where h is going because it has a constant 1. Notice that these one-sided derivatives are not equal. So the absolute derivative in between doesn't exist. If we go back to the graph, the slope of the tangent lines are constantly positive along this linear piece. And the slope of the tangent lines are constantly negative on this linear piece. And at the infinitely small transition point, there is no derivative. It's not 0, it's not either negative 1 or 1. We say it's non-differentiable at 0. And indeed, where one-sided derivatives are not equal, we can conclude that there is no derivative. A function will also not be differentiable where it's not defined, like horizontal asymptotes, and often a function is not defined where it has various forms of discontinuity. And in fact, a function is not differentiable at any location that has a discontinuity. Corners like this, the one-sided derivatives are not equal, which is why it's not differentiable, but corners are continuous. So we need to include them in our considerations.